Hello, everyone. Hi, distance delegates. So tonight, we are going to essentially bring together, the main idea here is that we're going to bring together everything we've seen so far in terms of valuation. Well, not quite everything. We are going to bring together the binomial model, the PDE approach, and the martingale approach that we saw yesterday. And our starting point is going to be the binomial model because we are going to be able to do a lot of things with just simple addition, subtraction, division. And you will see that when you have the binomial model, as the model is so simple, even change of measure can be done very easily without using big, huge result. So this way we can focus on the idea rather than be bogged down in the technique. But just before we do that, there is one part that we didn't cover last night, because we already covered a lot of things, and that's Feynman-Katz. And Feynman-Katz is really, I would say, halfway between what we did yesterday and what we are doing today, which is why it was located at the end of the notes last night. So Feynman-Katz is a very nice result because it enables you to look at a problem and write down two interpretations for it, one as an expectation and the other one as a PDE. Actually, historically speaking, it was, Richard Feynman devised this little result, and you will see it's actually quite closely connected to the Kolmogorov equation. He devised this little result in the 1940s while working on the Manhattan Project because he had some fairly large PDEs to solve numerically. And in those days, you really didn't have powerful computers, so he was stuck. So he found a way to bring it back to an expectation. And then using Monte Carlo methods, that's where Monte Carlo methods actually really come from, using random numbers generated or published by casinos, because casinos are required to publish their roulette numbers just to show that they are not cheating with their own roulette. So using roulette numbers as random numbers, that's actually as close as you can get to real random number generation, he was able to solve these PDEs by probabilistic methods. So that's why the formulation that you're going to find in most textbooks goes from the PDE to the expectation, but actually this door works both ways. If you've got an expectation, you can reformulate it as a PDE. So it's one of the most useful results. There are really three key results when you're dealing with stochastic processes. The first one, of course, is Ito, gold medal winner since the 1940s, year after year. Then you've got change of measure, of course. And right behind the underdog that's always fighting for second place is actually Feynman-Katz. And personally, I find Feynman-Katz is more helpful than change of measure. So the two are helpful in different contexts, but I find that Feynman-Katz is really very helpful. And it's a little bit understated because PDE people don't tend to like it much as it brings them into probability theory, which they may not be comfortable with. And probability people don't like it much because it brings them into PDEs, which they are not necessarily comfortable with. But for you guys, it's actually a very nice advantage to know that there is this swing door, because if you get stuck in a corner with an expectation and you feel that you could crack it more easily as a PDE, then you can just Feynman-Katz it into a PDE and case closed. Similarly, if you've got a PDE and you're stuck there, your numerical solver doesn't work, or you need to think in higher dimensions, meaning with more products, for example, which PDEs don't do very well, then you can transform it into an expectation and play with that. So here is the Feynman-Katz result. We assume that, and that's what's on my slide, so I'm just copying what's on my slide from last night. VTS solves the boundary problem. So we start from PDE to go to expectation, but it works both ways. Boundary value problem. Del V del T, TS, plus mu TS del V del S, evaluated at TS, plus 1/2 of sigma squared as a function of TS del 2V del S2 minus RV TS is equal to 0 and subject to terminal condition. So it's a boundary value problem. VTS is some function of S. So you see, it's really your parabolic, it's your standard parabolic equation. You know what you need to replace to get Black-Scholes. You've got RS here. This would be sigma squared S squared. Here, that's the discounting term. And here, you would have the payoff.
When you say the S is half sigma squared, so then sigma S squared?
Oh, the sigma and mu are two functions of.
In the next one.
Yeah, this is a function. So this is a function of TNS. Okay, so in Black-Scholes, you would choose the function sigma squared to be sigma squared of TNS is actually sigma squared of S, which is some constant times S squared. Okay, the variance times S squared. And that the process S follows the dynamics dst is equal to mu ts dt plus sigma ts dxt, where xt is your usual Brownian motion. Then the function f, the function v has the following representation. V evaluated at t and some value of s at time t is equal to e to the minus rt minus t times the expected value of your terminal condition given information to time little t. So you see, part one is the boundary value problem. Then we introduce this idea that we can have a probabilistic interpretation by just saying that S evolves dynamically, and then you've got your interpretation as an expectation. So if you want to go, that's to go one way, from PDE to probability. To go from probability to PDE, in probability, you will necessarily have that to start with, and then you can interpret it as a boundary value problem. So in the case of Black-Scholes, we find our two key results from our first, from our two Black-Scholes lecture, which is that del V del T plus RS del V del S plus 1/2 of sigma squared S squared del 2V del S squared minus RV equals 0, and V at terminal time is equal to the maximum of ST minus E or 0. Then you start from this boundary value problem. You say, okay, I can get a probabilistic interpretation for that. So I set up some process S for my state variable. dst is equal, and here I just read rs dt plus take the square root of the diffusion term, sigma s dx And here, we know now, so I'm just going to put a dot here, T. I put a red dot here because when you go from PDE to expectation, some of the information gets lost. Okay? And same thing when you go from expectation to PDE, some of the information gets lost. So you'll have to reconstruct it. If you go from PDE to expectation, one of the information that gets lost, and that's actually a common mistake even in some textbook, is that when you go from PDE to expectation, it doesn't tell you where you are, what's the measure, right? We know now that it's the Q measure because the drift is the risk-neutral drift, right? So that should be the equivalent martingale measure. It's not the physical measure. But the idea of measure doesn't appear anywhere in Feldman-Katz. Feldman-Katz says, well, this problem that you solve, I don't care where you solved it. You solved it. Now we just create a Brownian motion somewhere in some space omega f plus a measure. We just write out the dynamics, and then we can solve it as an expectation. So here, Vt s at time t will be equal to e to the minus rt minus t times the expected value of future cash flows of max of s t minus e or 0, conditional on information to time little t. And this expectation here, again, we need to specify where it is. And that's not specified in Feldman-Katz. So mechanically, it works. But you've got to be careful with the fact that Feldman-Katz doesn't tell you in which measure you are. So it's very, one of the common mistakes would be to take several processes that are derived under different measures and just Feldman-Katz them so that you've got several expectations. Just treat that as, oh, it's the same process under the same measure. Well, it might not be, okay? On the other hand, if you go from this to the PDE, you're going to lose a bit of information. The information that you lose is the information about hedging. When you set up your PDE, by going forward with the PDE, you got naturally the interpretation that this is the delta. So that's how you're going to hedge your option. This is the gamma. That's how you're going to hedge the convexity of your option. And that's theta. So you get that naturally by going through the PDE. If you start from the expectation here under the Q measure and you move there, the interpretation of del V del S, del 2V, del S2, and del V del T is not immediately obvious. You need to think a bit about it. Okay? So it's very convenient computationally, but you've got to be careful because it's just a computational result. Okay? It doesn't carry the full story in itself. It's an interesting door to go from one room to the other, but if you don't know what to expect in the other room, you've got to be a little bit careful in terms of thinking about what these are and what these are. Okay? Hi, Deepak. Yes, exactly. So in my notation from earlier on when I wrote mu, could write it nicely. When I wrote mu ts, here in Black-Scholes that would be rs, so there is no time dependence. And when I wrote the function sigma ts, here that would be sigma s. So here again, no time dependence necessary. And here sigma is so a constant, while here I've basically overloaded my sigma. Here that's a function. So the main objective tonight is going to be to look at the binomial model, the PDE approach, the martingale approach, and try to figure out why, with proper parameterization, the three give us the Black-Scholes equation. Two spoilers. One, it's not by accident, but I think you figured that out already. And two, it's not because we tricked it into giving us the Black-Scholes equation. Okay, it's not because we force any of these approach to give us what the PDE would give us. So, to unravel how all these things are connected, let's go back to what we know. And what we know, our starting point, was the binomial model. So here again, always read the label before using any model. For the binomial model, it's not a great model of asset behavior, really not. It's certainly not a great numerical method. It probably was a great numerical method about 350 years ago, but not anymore. And but it's one of the best ways of understanding how various asset pricing techniques interact, because we can clear up all of the technicalities. So just to review a little bit the one period setup, because that's going to be our starting point. We'll move into multi-period when we need it. We start at time 0, and we've got a stock, and the stock is priced at S0. And then there are two possibilities with probability P and 1 minus P in the physical world. The stock could go up to a value SU, which is U multiplied by S0, or it could go down to a value SD, which is a little coefficient D multiplied by S0. Now, up means up and down means down, meaning that up needs to be greater than 1 and down less than 1. And then we look at the time frame, and we call the time frame delta t for now. So we've got a time period delta t. And we, of course, as well in finance, we need to introduce discount rate and discounting from delta t back to now. So right now, as we are in discrete time, one period model, etc., our discount rate called D is just 1 over 1 plus R delta T. And D inverse, 1 over D, which we are also going to call B for the bond price, is therefore, or the bond return is 1 plus R delta T. Our objective is to find the current value of an option, and we did it two different ways. So the first way was delta hedging, and the other way was risk neutral valuation. So for delta hedging, that was quite simple. The recipe goes as follows. Create a hedged portfolio. Let's call it pi. And this hedged portfolio is long an option, short delta stocks, where delta is the number of shares. So that gives you something like that. P0, PU is equal to VU minus delta SU. So delta is fixed for a time period. Pi D is equal to VD minus delta SD. Now, our objective is to eliminate risk. So we peak delta to ensure that pi u is equal to pi d. if pi u is equal to pi d, we no longer have a binomial tree or a binomial branch. All we've got is this, pi 0 and pi delta t, right? We've got certainty. Risk has been eliminated. So start from pi u is equal to pi d, which means vu minus delta su is equal to vd minus delta sd, which gives you vu minus delta u s0 is equal to vd minus delta d s0. So when you solve for delta, you've got delta is equal to vu minus vd divided by u minus d times s0. So that's the number of shares that you need to short in order to hedge your option. Now, you've managed to eliminate risk. Congratulations. But that means that as your portfolio is risk-free, then to prevent arbitrage, so now your portfolio is risk-free, so to prevent arbitrage, it must earn the risk-free rate. Which means that if you look in time, you've got pi 0 here, pi delta t, which is the same thing as pi u, same thing as pi d at time delta t. Well, you should be indifferent between taking an amount of money, pi 0, and investing it in the strategy, or taking an amount of money, pi 0, and investing it at the risk-free rate, therefore earning pi 0 multiplied by 1 plus r delta t. So this is the same thing as 1 over d, or b. Now, equating pi 0 divided by d and, for example, pi u, you get 1 over d v0, which is what you're trying to find, what I want to find. Minus 1 over d, minus 1 over d delta S0 is equal to, for example, Vu minus delta Su. So now just plug the value for delta, which is Vu minus Vd divided by U minus D times S0. Rewrite this as U S0. Do a bit of cleanup. And the solution is there. So here, go to slide 9, equation 1. So V0 is 1 minus dd times Vu minus du minus 1 times Vd divided by U minus D. So that was delta hedging. And you see that it's exactly the same mechanics, whether you do it with the binomial model or the PDE. It's exactly the same logic, the same steps that you go through. Now, the other way of looking at things was by dreaming of a different world. Not necessarily a better world, but dreaming of a different world. So that gave us the risk-neutral pricing, the idea of risk-neutral pricing. So imagine a world, the risk-neutral world, where everybody is neutral with respect to risk, meaning they just don't care about risk. Risk has not entered their wildest dreams or nightmares. So whether they are going to do bungee jumping with or without the bungee, they would pay the same amount, right? That's the risk-neutral world. Regardless of the type of risk that you take, on average, you're always going to earn the risk-free rate if you survive. Okay? So that's risk-neutral pricing, meaning that in the risk-neutral world, you do not get a compensation for the risk that you take. On average, all the assets grow at the risk-free rate. In particular, the stock must grow at the risk-free rate. Here again, on average. So you should be indifferent between putting S0, investing S0 for a time delta t and investing it at the risk-free rate so that it earns S0 times 1 plus R delta t, which is 1 over d times S0, or taking the expected value with respect to the probabilities on this beautiful risk-neutral planet, of your stock at time t. So either you invest this amount as 0 in the risk-free rate, or you invest it in the stock, you should get exactly the same thing. Now, we are in a binomial model, so the expectation is actually pretty easy to compute. Let's call this the risk-neutral probability P star. So the probability on the risk-neutral planet is P star. And we've got, therefore, an expectation which is P star times the upstate, U as 0, plus 1 minus P star times the downstate, D as 0. So now, eliminate the S0s, cancel them. Then switch around the D and solve for P star, and you found that P star is equal to 1 over D minus D divided by U minus D. So that's your risk-neutral probability of an up move. And from there, we could apply the same logic to the option and price the option with exactly the same formula, except that now for the option, we know what the probability is, so we can use the same formula to solve for V0. So what we did was that. We just said, OK, the same thing goes for the option. So 1 over D times V0 is the expected value in the risk-neutral world of your option price, so your payoff, meaning that V0 is equal to D P star that we computed earlier. So P star is equal to 1 over D minus D divided by U minus D times the value, the payoff in the upstate, plus 1 minus P star times the payoff in the downstate. So now we are here. Yeah, we are here. So in our little chart at the beginning, when we start to expand on this diagram, the first thing is to say, okay, here let's go for delta hedging. That's the first method. And here, risk-neutral valuation. And in both cases, we get the same value for the option. Remember, that's a trick, especially for exams. Use your favorite method to find V0 and check it with the other method. If the two V0s disagree, then there's a problem with your calculation. So the first link between the two methods actually is going to come in right now. The first link is actually quite easy. You can tie in delta hedging and risk-neutral valuation by restarting from delta hedging and noticing that actually equation 1 here, well, when you pick these together, 1 minus D times D divided by U minus D, that's essentially D times 1 over D minus D divided by U minus D, which is D times P star. And same thing when you take that, du minus 1 over U minus D, that's D times 1 minus P star. So that means that you can rewrite this formula as D multiplied by P star VU plus 1 minus P star VD. So the delta hedging formula contains inside your risk-neutral formula.